there are a couple of things that I wear the hats off. I wear many hats. In addition to working for CodePlay, I've been chairing the SYCL language group for about 3 years now, but I also have another hat. I'm also deeply involved in the C++ standard committee, partly with the setting the directions for C++ standard. I guess that's because I'm very old, and although I don't look it, but I am. I've been there for about 20 years participating in C++. I had many features in C++11. Aside from that, I was also the head of the CEO of OpenMP for about 5 years, especially during the times when we were trying to add accelerator support into OpenMP, starting with 4.1, 4.5, and 5.0. So I no longer do OpenMP, but I continue to serve on the C++ standard committee. And my vision, I think, out of all this slide, and after this, you can all go home. No, seriously, there's some great talks. Stay and listen to them. My vision is try to unify SYCL and C++ so that ultimately, at some point in the future, they become one. So let's see how that works out, okay? So these slides come from many, many people, and I really want to make sure I thank them. Any error that are left are totally theirs. It's not my fault, okay? No, really, they're my fault. All right, so I always think of break up my talk into 3 pieces. I'm going to go through and talk about, is ISO C++ going heterogeneous? I'm going to talk about, is SYCL gaining in the marketplace? I'm going to talk about, is there a direction for C++ and SYCL? And because I have so many slides, I will warn you, I will skip over some detailed slides. It is a keynote, and I'm not supposed to show codes, right? I'm not supposed to show any code, but there is code in here, and because I'm that kind of a guy, I still like to look at code. So this slide is about what gets me excited in the morning, what gets me up, and it's not my cat, okay? I'm told that in any kind of talk, showing a lot of cat pictures is usually, there's nothing wrong with that, okay? All right, so I've been in C++ a long, long time, and out of that, I've been involved with C++11 for 10 years before it came out. And out of that, and since then, we have learned a lot of heuristics that we know, leading to guidelines about C++, modern C++ programming. And I can pretty much distill it down to these 7 or 8. Starting C++11 and onward, I kind of call it the no more raw food syndrome. The idea is that you shouldn't be using raw numbers. You should use type-rich programming like user-defined literals. The fact that you shouldn't be declaring, you should use auto. The fact that you shouldn't use null, you should use null putter. That you shouldn't use raw, new, and delete. You should be using some kind of unique putter and share putter. No more heap allocated arrays, you should use std vector and std string. That you shouldn't use functors, you should use lambdas. That you shouldn't use raw loops, you should use STL algorithms or range-based for loops. You could even turn a lambda into a loop if you have to. Then, of course, there's this thing called the rule of 3. If you were in C++ 03 days, you remember this idea of you always have to have a constructor, copy constructor, and destructor, assignment operator, things like that. That has now turned into what's called the rule of 0. If you have a value type, you shouldn't need any more additional special operators. And what's called otherwise, if you have a fully polymorphic type, you need to know about the rule of 5. Google it, look it up. I'm not going to talk about it anymore about that. But if you can't figure it out, talk to Matteo or Daniel. I'm sure they will tell you what these things are. The other thing that I'm deeply passionate about is parallelism and concurrency and heterogeneous programming. So in C++, the rule with parallelism is, of course, use the right abstraction. But it's complicated. Which abstraction do you mean? Well, I can tell you that C++ doesn't fill everything there is in this space. It fills some. So for cores and hardware threads, you should start using C++ 11, 14, 17 threads. You could use async instead of the standard threads. You could use, but you can't use anything. There's nothing to support vectors yet. Okay? Sorry. You have to use some vendor things. If you have atomics and fences, there's some smattering of supports there. If you want to use parallel loops, again, until C++17 parallel algorithm, you didn't have parallel loops. So that's why you have to use OpenMP. If you had to use heterogeneous programming, sorry, there's just nothing there. Okay? You had to use something else. And that would mean OpenCL or HSA or SYCL, Coco's, I know pretty much all of them. I've been doing this for a long, long time, and I've covered almost every parallel heterogeneous programming model that there are. You want to do distributed node programming? You can't. Okay, it's just not in C++ to do it. You have to use MPI or UPC++. But there's this thing called HPX that is very modern C++ that you could do for distributed node programming. You want to do cache, you want to control the fault sharing. Since C++17, there is a fault sharing feature, okay? For you to prevent overlapping layering of access. Look it up, you'll find it. There's no way to control NUMA access, and there's no way to have GPU of local storage. And right now, exception handling is still only single-threaded, okay? It does not have concurrent exception handling support. We're going to have that we're going to need solutions for these. And this talk will talk about some of the attempts that I've been working with the committee with a lot of people's help towards that direction. So what are we talking about? So by now you should know that it's not just about performance and portability. It's about productivity and what I call the iron triangle of parallel programming nirvana. In short, you can pretty much, as a language designer, and I've been a language designer for 25 years. It was a terrible one initially, but you know, everybody is terrible at the beginning. And I'm getting better, and I think I'm probably beginning to reach my peak now. So you're catching me at the right time. You can really only optimize two of these things at any time. It is impossible, I think, to optimize perfect performance, portability, and productivity. What does that mean? Well, here's an example. I'll pick 4, OpenCL, OpenMP, CUDA, and SYCL, okay? So the truth of it is that now there are languages that pretty much give you access to a lot of the speed in your machine. All those things I talked about a couple of slides ago, there are languages that give you almost all of those things now. Not C++, but they are. So OpenCL is pretty much C-like. It's assumed to be pretty low level, but it's highly performant. And as such, generally, it might have lower productivity than a C++ language. But it's very portable because it uses cleverly SPIR-V and all that. OpenMP, of course, works for multiple languages, C, C++, and Fortran, using compiler directives. And this makes it easy to use. So it's pretty high productivity, in my view. And because it's based on 3 general purpose programming languages, it's pretty portable too. Later on, I'll show you that there's now a performance portability benchmark which shows OpenMP indeed is one of the most portable. All that means is more compilers supports it, okay? CUDA is great, but it only works with one device, and it's very specific to one device, so it yields excellent performance. But its productivity is improving, but I dare say it's not all that portable. I'm not going to run it on an Intel device, on AMD device, although AMD is trying with HIP. SYCL builds on top of OpenCL and C++ as a foundation, so as such, it tries to inherit the portability and the performance aspect and tries to reach that pinnacle of having some amount of productivity. So we're going to talk a little bit about all of that. So in my world, there's always been talk about the difference between concurrency and parallelism. Probably the best way to think about it, without me diving into actual technical science, computer science term, and I could, is that if you think about a basketball game, that is concurrent. You got to be passing balls between people, stopping them. You know, that's a mutex, for instance. You might have to pass a message back and forth to your teammate. If you're running in a track meet, that is parallel. I dare say that C++ standard, most of the features there are for concurrent programming. Very little features there are for parallel programming. As such, it's not all that great for you guys for high-performance computing. But we can make that better, okay? So what's in C++ for parallel programming? Well, I've been charting this for the last 20 years. And periodically, I've shown these slides about the state. I always try to separate out into 3 or 4 categories: asynchronous agents, concurrent collections, mutable shared states, and recently I added a 4th, because the 4th just doesn't quite fit any of the other 3, heterogeneous programming. So asynchronous agent is tasks that runs independently and communicate through messages. So examples are like GPU, GUI backgrounds, printing. If you're on your screen and you want to press something to go print, you want that to be an asynchronous agent to go off to the printing. You don't want your screen to suddenly freeze up while waiting for that printer to finish, right? That's an asynchronous agent. You guys all know what it is when I say it like that. Concurrent collections are operations on groups of things so that you can exploit parallelism, straight through parallelism. Trees, quick sorts, the key metric we think about is throughput. Mutable shared state is about avoiding data races and synchronizing objects in shared memory. That is real concurrency, okay? We're talking about locked data structures, we're talking about atomics, okay? We're talking about race-free and lock-free programming. Heterogeneous programming, well, you guys kind of all know what this is because this is GPU day, and it's all about offload. People have different words for it: dispatch, pipeline, dispatch, offload to other nodes. Those nodes might be small nodes like a GPU, or maybe a fully loaded node like a full CPU. Before C++11, at the bottom, you'll see that the only way you could program that was not C++. You had to use POSIX thread, you had to use Win32 threads, you had to use TBB, you had to use some sort of lock systems of vendor intrinsics. And of course, even before C++11, that's why they started to have OpenCL and CUDA, because C++ didn't have any of these things, and C didn't either. After C++11, you see in the red that I started categorizing the C++11 features that serve these domains. Some features would serve multiple domains, okay? So for the most part, you have things like threads, lambdas, and lambda functions and thread local storage that serves asynchronous agents, okay? And maybe you might even argue that to some extent, the promises futures can serve concurrent collections, but actually it wasn't really that much. It didn't really serve it all that well. And finally, on the mutable shared states, because C++11 was the first C++ that had to interact with old C++, that legacy C++ that did not have parallelism, which meant they had lots of global variables, which meant you really have to control access. So there was a lot of work to add things like mutexes and condition variables and atomics and how to do static initializations and termination. Whoa, what's this? There's something for heterogeneous programming? I claim that C++11 lambda, and back then it was called the monomorphic lambda, was key to opening the ability to dispatch. In fact, I remember when we designed it, and I was there, we distinctly discussed the idea that we want to be able to offload this to a different thread, okay? Perhaps a lightweight thread. So what does C++14 added? Not much, okay? We made polymorphic lambdas, we call them generic lambdas, nothing for concurrent collection. I told you there's very little for parallelism. And then we added even more for mutable shared states, okay? We had this thing called out of thin air, okay? This is a really esoteric memory model thing that I really don't want to get into. We didn't add much. 14 was really a kind of a fix-up release. 17, we added loads more stuff, okay? We added parallel STL, okay? That, I think, is the biggest improvement for C++17. But we continue to add more things for shared memory, okay? Controlling shared memory access, scope lock, shared mutex, ordering of memory models, progress guarantees. TOE stands for thread of execution, okay? And execution policies. Now, I would argue that progress guarantees, TOE and execution policy now sets another foundation change to allow us to enable. They didn't give you heterogeneous, but they were key enablers. Why? Because one of the things about C++ is we talk about stood thread. It's a very heavyweight thread with a full stack. This is not what GPU threads look like. So by changing the term to TOE, threads of execution, now you enable both either stood thread or lightweight threads with a very, very thin stack. Progress guarantees. Up till that point, there was no specific things about how to guarantee progress guarantees in C++. But that's not going to work for GPUs because GPU has a very weak progress guarantee. And that had to be enshrined in somehow so that the C++ standard make it available. Now, all we did was that we said that now there are these things called progress guarantees, and there's different levels of progress guarantees called strong and weak, okay? And now we can say, well, some things have a very weak progress guarantee. We have these things now called execution policies, and that's mostly was for sequential and parallel execution policies, but there was actually an escape clause in there that we use, which allow you to escape and apply the execution policy to heterogeneous programming. Okay, so what does the C++ standard look like? I'm going to check my time just to make sure, because it's a big group now. You'll see that it's now up to 20 study groups. We've added things like, so I'm involved with the directions group, the low latency group, and the machine learning group. But there are also groups for tooling. Now we are thinking about build systems, okay? We really think that that's one of the big things C++ need is command of the build system and dependency handling. There's also text processing, which is under Unicode. There is an incubator for EWG and LEWG so that they can process paper at a high level before they get passed to the actual EWG and LEWG. Machine learning, I can tell you a lot about that because we're trying to add papers on statistical functions, mathematical functions, and how to do differential calculus libraries to C++. I'm loving this stuff. Education, isn't it high time that we have a standardized way to teach C++, especially with so many complaints about how complicated it is, okay? What does C++ look like right now? This is a snapshot of where we are. Next week, I'm glad that you guys invited me here this week. In fact, I apologize for these particular, because I think they would probably move because of me, because these were the only days I was available. And right after this, I'm going to go to Cologne on Saturday to attend the final C++ standard meeting where features are going to be closed for release in the C++ 20. After that meeting, we will release a C++ committee draft for public review and comments by every national body. Now, I don't know if Hungary has a national body, but if you don't have a channel for that, I will be happy to channel your comments, okay? All of this is just saying there are lots of study groups driving things in. I'm not going to go through them too much because I'm going to go through them in a little bit detail. Before C++ 11, we had a bunch of things that had to do with the technical report on C++ library extension that we adapted in. Then we had things like floating point, which didn't go in, and special math, which did go in. Let's take a look at what's going on with some of the major projects. I won't stop on too many of these unless you guys ask me questions, okay? Because this is necessarily going to be just a really fast overview. So the things that we wish would have made it into C++ 20 was executors. That would have been another key step towards heterogeneous programming, the ability to dispatch functions to any particular resource, okay? Why it didn't make it? Huge story there. Coroutines made it. Reflections was never meant to be going in, but it's going to go in around 23, we think. The one thing that we got in was concepts, okay? And that was important. The one thing that we were struggling to get in last minute was this thing called abbreviated function template syntax. We got the full concept function function template syntax in, but this is a short form, and this is basically a compromise because with this syntax, these abbreviated function template, AFTs, look like this, basically void F of a concept auto X. And this means that both I want to write a function template without the template angle bracket notation, and the camp that says I want to be able to tell syntactically if a function is a template are both happy at this point. Okay? Because here, okay, because here you can see that because of the auto, it tells you that the parameter has a deduced type, and therefore the function has to be a template. Okay. You can also use concept auto as a return type, as in the second example, and as the type of a variable. And in each case, the type's deduced, and the deduced type has to satisfy the concept. Okay? So that was principally our solution. Other things that made it through, most of concurrency is now into C++ 20. So these are things like latches, atomic share putter were merged in. We have usage experience in a few cases on these things. Ranges has been merged into C++ 20. That's a big movement towards moving us away from having iterators. Networking did not make it. That was bad. We are now have to moving that into C++ 23. Modules made it. Contracts made it. Numerics, these are all other things that are under development. Numerics, concurrency, parallelism, transactional memory. There's a graphics TS now, and library fundamental 3. Now here's a really interesting one. There's now two proposals for linear algebra. Okay, that's coming through my group, SG14. And they are describing what you would expect, the ability to do matrix computation. This is the foundations for machine learning. But it's also a foundation for games programming and high-performance computing. So yes, the high-performance computing is now really driving their features in. Machine learning, we're talking about how to do graph node data structures. We're talking about how to do statistical mathematical functions. Would you believe that C++ standard has no mean or variance mathematical capabilities? Even though I've been involved in it for years, I didn't realize that. We're talking about how to do differentiable calculus, okay? Pattern matching, that's going to be very popular as well too. We're also working to make C++ safe, because we're seeing C++ being used in safety critical domains increasingly. In fact, AutoSAR has actually set C++ as the default language for autonomous driving. That's a big vote of confidence for C++. And that's why there's this huge drive to make C++ safe, and in collaboration with MISRA, with AutoSAR. MISRA is the usual motor vehicle safety group. The education I talked about, there's now audio. There is a group doing Unicode, and there's now, as I said, doing tooling ecosystems. All right. I'm not going to go through every one of these. I leave these on the slides because it's a listing of all the C++ 20 features that's in the language. They're linked to the paper, so when you click on them, you will get the actual paper. That class will be like a whole year class to go through all of that. All right, so what do we get out of parallel concurrency for C++ 20? All right, we get SIMD vector, finally. We got a lot more mutable shared state stuff. We get J threads. These are joinable threads, as opposed to the current threads, which do not join when you finish the program, which causes detached zombie daemons lying around. Okay? We have coroutines, which is basically a generalization of a procedure call. But in this case, you can enter and exit function many times and resume. We have atomic underscore references, which is, I dare say, is another heterogeneous C++ feature, okay? So let's take a look at what SYCL is. Just step back for a moment and see what SYCL is. Is it winning in the marketplace of heterogeneous programming? So when I was the CEO of OpenMP, I've always wondered why high-performance computing and consumer computing never use the same parallel programming language. Over time, if there was a chance at convergence, maybe if we could just focus on one language, like C++, I figured this is the one language that is shared between high-performance computing, games, finance, manufacturing. So, or maybe I was just colorblind by my love of C++, but I really wanted to see if I could merge those two. And so that we could focus on just one language and making that beautiful and productive. And in fact, I claim now that the big bang of C++ heterogeneous framework has already occurred because there's lots of them now. Where the training wheels have basically all come off, and we're now deeply exploring the complexity of the four horsemen of heterogeneous computing. I have another talk at LLVM last year that talks about the four horsemen that we always have to deal with. I'm not going to talk about them now because that would be a whole hour. We're now beginning to wonder when and how to do it in a performance portable manner. And that's, we think, is the next closest nirvana. And because it's done in a very quiet way using other features that are good for CPUs on the ISO C++ standard, I call it the quiet revolution. You will not see a big template, a big technical specification that says heterogeneous. And yet, many people on the committee share my dream, and we work collaboratively to get it in that direction. You can tell by the kind of people who are on the committee, NVIDIA, AMD, Intel, all the DOE labs are now all present on the committee, okay, Codeplay. We're all trying very hard to collaborate quietly without subverting the rest. Why are we doing that? Because C++ is a huge committee. The people who are interested in parallel computing is like maybe about 30% of that huge group. Most people there are interested in R-value references and modules. They don't care about parallel computing. Of that 30% that's interested in parallel computing, only about, say, 10% are interested in heterogeneous computing. So that's why we kind of have to do it a little bit quietly. So the time is now, I would say, this is the right time to try adding this to C++. If we have multi-core CPU parallelism in C++, why don't we have it for heterogeneous? Because even despite all the learning experience we have, it's still not easy. There are so many pitfalls, so many new ways that now we're programming. I was at Hot Chips, and now today most chips are machine learning chips, AI chips, with multiple different kinds of CPU, multiple different kinds of GPUs, multiple different power profiles. They're very, very complicated. So in the landscape of C++ heterogeneous computing, there really is a lot now. There was Boost Compute as a pure compute library. I worked on OpenMP. There's AMP. There's TBB. There's COCOS from Sandia National Lab, and which has been implemented for OpenMP threads and CUDA. There's Raja from Lawrence Livermore. There's Parallel SYCL, which is somewhat based on the AMD Bolt and the NVIDIA Thrust and the Microsoft Parallel Pattern Library. There's SYCL, okay, from the Chronos standard, which supports CPU, GPUs, and the gentleman before me, FPGAs. There's HPX from Louisiana State University, which is a distributed computing model using modern C++. There's CUDA, proprietary from NVIDIA. AMD has ROCm, HIP, and what they call the HCC compiler, which is C++ AMP-based for heterogeneous computing. And NVIDIA research has always been working on something called agency. I'm not going to go through all of these, obviously, but I'm going to focus on SYCL. Just as a quick primer, so what is SYCL? Just imagine, so C++ standard does not explicitly have heterogeneous computing, but its foundation is fantastic. It's modern C++, it's got templates. We want to hook in the heterogeneous computing aspect using OpenCL foundation so that now you can distribute to any particular, many different kinds of devices. And the other key importance is we also want to make sure you separate concerns of where and how you do the computing. This was the real, in my personal opinion, the problem with OpenMP, is that it conflates the concern all into a single pragma. That one pragma tells you where you're going to execute it, how you're going to execute it. That is just simply not how C++ want to do things. Okay? So the key is not creating a language that is restricted. So there's this thing called OpenCL C++, and it didn't work well with templates, and that's just not going to work all that great, right? So So why do we have a new standard? There's this running joke that we want to pull in all the standards and make one. Well, at the end, you always end up just adding n+1 standards. So how does SYCL fit in? Well, we like it to fit in so that you can have any kind of C++ template libraries, which is where most C++ is. And now you can use SYCL, and then you can use OpenCL underneath to dispatch to any particular hardware. Okay? With SYCL, we don't add any language extensions. We're going to work with existing C++ compiler, and we're going to provide the full OpenCL feature sets. The ecosystem is quite large. We have SYCL Parallel STL. We have SYCL BLAST. I forgot to add SYCL machine learning and DNN for deep neural networks. We have it for Parallel STL with ranges. We have CUDA to SYCL conversions. We're also working on SYCL reference, similar to CPP reference, which is a great online guide. Today, there are more things than ever because University of Bristol has these heterogeneous benchmarks that they're running. And they've tested them for various heterogeneous programming language. And then they assign what's called a performance portability number, a PP number, to say how performance portable something is. That's something you should take a look at. We have Intel's parallel research kernel to find out how productive this change is. Is it problematic converting your existing code to SYCL? They said it's fantastic. It's actually very difficult to convert code to boost.compute in some ways. That's their conclusion. Adapting to workloads now in HPC, machine learning, and vision. So one of the things that I did, but I probably won't have time, is talk about SYCL past and future using the Charles Dickens novel, with apologies to him. I have a good story, not a bleak story. SYCL is definitely vibrant and growing, and we're now tightening the ISO C++ alignment, injecting our heterogeneous knowledge into ISO and adapting C++ features from ISO, okay? We have this thing called the Distributed and Heterogeneous Programming Workshop, okay, that is paired with iWACL. And this is going strong. It's essentially a gathering of heterogeneous programming language, like SYCL, like COCOs, like HPX, like Raja, and C++, to try to discuss the kind of learnings and things that we need to do to improve them. We released SYCL 1.2.1, okay? So that was before, in the past, in 2015, we released SYCL 1.2, which was based on a C++11 programming model, and that was based on OpenCL 2.1. Our observation back then was that heterogeneous and C++ is coming together, but a lot of people didn't know OpenCL all that well at that time. They still don't. So thanks to Mate and Daniel, you guys are building this OpenCL primer. Thank you very much. The ghost of SYCL present, we're now into the current release, which is SYCL 1.2.1, based on OpenCL 2.2, okay? And right now, SYCL 1.2.1, we are open sourcing the CTS. The CTS is Conformance Test Suite, so that you guys can all have access to it. In SYCL 2019, we've started removing SYCL 2.2 because it had gone forward too far ahead with no implementation, and we want to pull it back and set a more realistic target. We have a lot more implementations, so instead of what was 1 or 2 implementations, we now have the Clang Intel implementations, my company's Compute CPP proprietary implementations, aiming specifically for AMD, Intel, and NVIDIA devices, but also for self-driving car. Tricycle, which is for FPGAs, HipSYCL for ROCm, and then there was a student who did SYCL GTX. We ended up hiring him, so there goes another implementation. There's a lot of participation on the call. As my host mentioned, Wigner has entrance now on the group. There's like easily 10 or 20 people on the call now. And we are planning to have SYCL balls at supercomputing at ISC and classes at CPPCon 2019, supercomputing and ISC next year. Even though it's called 1.2.1, there was a lot of changes. We added things like vec load and store operations. We added things like variadic functions for getting kernel arguments for OpenCL, interoperability. We added placeholder accessors. We added reinterpretable buffers and explicit copy operations. I have slides that has code, but as this is a keynote, I'm not allowed to talk code. So I'm going to skip past these guys. And the feedback from SYCL 1.2.1 is that it's very well received by the C++ community. The majority of people still didn't understand the limitations of GPUs, and SYCL allows you to access the GPUs. Some prefer migrating CUDA to SYCL than OpenCL. because it's open source templates and has asynchronous features. So the last act of my talk is what is the future direction? Well, let me just say that for SYCL future, we instead of creating these odd 1.2.1, 1.2 names, we've changed it to match kind of like C++. So now the next one that we're planning to go is SYCL 2019. Every 3 years, we plan to put out a SYCL release to match the rapid requests that the users are needing. And that way we can match, so that 2019 uses the C++ 17 base, and SYCL 2021 would use the C++ 20 base, because we're deeply involved with C++, we know where they're going to be. The work on 2019 is already starting. We introduced a new naming scheme, as I talked about. We're aiming for a regular bus train model, where C++ standard is going for 3 years, we're going for 1.5. We're going to build on SYCL 121 and add user requests. We might add safety critical features, and of course, title alignment. SYCL 2.2 is released. And so I'm gonna move a little bit through all of this stuff, because most of this stuff is talking about what is in SYCL that's from different groups, because I want to get to where C++ is as my last bit. So for a long time, C++ was kind of like Brownian motion. Where it went, depending on how many hands was on the Ouija board. You actually couldn't tell where it was going. About 3 years ago, we wrote this paper called P0939, which is a direction for ISO C++. And the idea is that when people come to us with big ideas for big change, we've always routinely told them that we prefer gradual change in C++ because it has millions of lines of code dependent on it. And the thing is that with C++ popularity these days, this is what it looks like now at a C++ standard meeting. There's just simply too many cooks in the kitchen. We expect about 150 people to show up in Cologne. The European meetings are usually much better attended than the US meetings, partly because Donald Trump and nobody can now go to the US legally anymore. I have a secret to tell you. The direction group sees C++ in danger of losing coherency because of the many proposals, the massive number of proposals that are going, and many of them contradictory. So switching my hat now, I'd like to point out that there is this mailing list now for the C++ standard, and the DG members are concerned with both the long-term and the short-term directions. So these are the DG members. It's a group that is essentially selected based on their years of history being on the standard, and I guess through that time they've shown a penchant for fairness, sometimes even against their own proposal, for the greater good of C++. And C++ has always had these ideals, like it's a language for defining and using lightweight abstractions, for building resource, for supporting large-scale software developments. It's pretty much succeeded, I would say, on almost all counts. But one of the things that it always has, and that's what this document lays out, is that it's a direct map to hardware, which was initially C, but now we think C++ filled that bill. And then there's also zero overhead abstractions. Now, we definitely want to strengthen 2 pillars, and that involves supporting modern hardware and more expressive, simpler, and safer abstraction mechanisms. And then finally, we have some concrete suggestions about things that we want to add. And you'll see that along this list, one of the most major ones is modern hardware. We need better support for modern hardware, and that's now enshrined in the direction document, specifically leading to heterogeneous and distributed computing support. So there you have it. I actually wrote that in myself, thank you. All right, so by the way, if you want to dive in where each of the C++ standard features is going, there is a GitHub you could actually now go to and track each paper's progress, okay? The takeaway is that C++ is pushing towards heterogeneous programming support. But C++ 20 is going to be a major release. What's going to be in 20? I've already mentioned a lot of these things like concepts, contracts, ranges, coroutines, modules, reflections, not executors, not networking, and we're not going to be able to add any additional features. With the new C++ 20, we now can fill in a few more lines. We will now have vector support, for instance. We will now have true, but that's still not enough. For the future, for things like heterogeneous, we're looking at things like affinity as a way of doing that. We're looking at executors as a way of adding NUMA support. We're looking at execution agent local storage to replace thread local storage. We're looking at reduction properties to cover concurrent exception handling. All right, this is talking a lot more about some of the details, but let's see what 23 will give us. The way I think of it is that for asynchronous agents, we're going to get networking, we're going to get asynchronous algorithms, maybe reactive programming. For concurrent collections, we're going to have a lot more for high-performance computing. New features, concurrent vectors, task blocks, unordered associative containers, two-way executors, and lazy sender receivers. For mutable shared state, we're going to have things like hazard pointers, snapshot, queues and counters, maybe transactional memory light. And then for heterogeneous, we're going to start seeing things like affinity pipelines, execution agent local storage, freestanding embedded support for machine learning and AI, MD span. These are going to be things that I'd like to see us getting in C++ 23. For C++ 23's non-parallel features, I want to point out that we want to start driving for a lot more libraries. We're going to try to have a lot less language changes. So library support for coroutines, executors, networking, okay? We need much more libraries. And many of these libraries can be improved. We have better reflection facility. And there's actually a paper that Biana and Gabby worked on called IPR that gives you this kind of better reflection representation. I'd like you guys, make sure that you guys refer to it. After C++ 23, we're going to be looking at reflection, more pattern matching ecosystem. So as you can see, just like C++ is a language standard, SYCL is just a language standard with many implementations, just like C++ has Clang, GCC, okay? And from the feedback from iWACL, we now know what we want to add to the C++ to SYCL in the future. And some of these things are being worked on by some of the folks from Wigner here, okay? SYCL is being investigated for high-performance computing now. I just gave a keynote at DOE. Xilinx FPGA and CodePlay demonstrated a PTX backend. We now plan a supercomputing 19 BOF. There's classes at CPPCon 2019, ISC, and supercomputing 2020, we think. SYCL has a dedicated, we're planning a dedicated SYCL conference in 2020. You heard of the Intel One API, the idea of data parallel computing C++. That is now potentially aiming directly at using just SYCL as the one API that they're talking about. And then finally, we need a lot more HPC features. Where does it end? It doesn't, because the idea is that C++, SYCL, and other heterogeneous parallel frameworks like COCOS and HPX are going to merge their learning experience together. Would perhaps SYCL continue to push forward as a reference implementation for new hardware. And with these new things, we can make sure that we can reach towards this heterogeneous future. How much time do I have? Am I done? 0 minutes, thank you. All right, I'm not going to show the video. The video just shows how you can do SYCL parallel STL very quickly and how it has a lot better speed than when it's done on CPU. Thanks very much.
Thank you, Michael. I'm actually very happy to see that now the way to HPC is paved both on hardware and software side. So, time for questions.
There's one question I wanted to ask, actually many, but I may just ask one. That the talk revolved very much around the relation of C++ and SYCL and how much of the knowledge in SYCL is being put into ISO C++. The current SYCL 1.2.1 standard takes a hard dependency on OpenCL.
Yeah.
And it was Neil Trevet who gave a talk at iWACL on OpenCL Next, how they are trying to modularize the API a bit more like Vulkan, so there are less mandatory features and a lot more fine-grained features so that it's easier to adopt and implement.
Okay.
And what do you see, what impact this OpenCL Next will have on either open source implementations of SYCL or OpenCL, or even vendor implementations of either? So what will be the impact of it on SYCL?
Yeah, so the question is, given the fact that OpenCL is now creating this OpenCL Next profile, where you can select certain features for support, for specific support for your embedded systems, how do we think that's going to impact SYCL? We think that's actually in line with where we think SYCL would like to go as well too. The other thing is that your other question was, given the fact that OpenCL is getting into this modularized back-end support, we are also looking at potentially detaching SYCL from totally dependent on OpenCL, such that now it opens the door for SYCL. There's nothing in SYCL that has to be dependent on actually OpenCL. It just rides on it because it's the most convenient heterogeneous platform there is. It could easily ride on Vulkan. It could easily ride on PTX, okay, ROCm, anything in particular, any kind of heterogeneous framework it could ride. In fact, today, SYCL is being experimented on at San Diego to ride on top of Cocos. The HPX people have taken SYCL to ride on top of HPX, okay? And I think this is just going to continue because they want to see if this kind of modern C++ framework that works with templates allows them to fit any kind of different backends there is. So I can tell you that work is already beginning. And because it's in the current release of SYCL, I can't promise it, okay? But being the chair of SYCL, I can tell you that definitely that there's work heading in that direction. Detaching from OpenCL just means that we just have to slowly detach it, write it out of the specification. Okay. Thank you. Thanks.
Okay, thank you. Further, a short question. Oh, it's nobody. People are too shy to ask, so maybe I can ask that. How about FPGAs?
FPGA is a key cornerstone for SYCL because we know that a lot of the machine learning capabilities are coming through in that direction. And indeed, you see that one of the implementation, Tricycle, is designed specifically for FPGAs. And with Intel, we work closely with Altera as well too. So both of the major FPGA vendors are trying to use it. Yeah, thank you.
Excellent. So let's thank Michael again.